Hello, I'm Jazad, and this is Lab 3 for Physics 2211. To introduce this lab, I'm working on analyzing the motion of an object around a black hole and use this analysis to determine the velocity needed for the object to orbit around the black hole and not get sucked into it. And the main purpose of this lab is to connect Newton's second law and momentum. So for the fundamental physics concepts, I use Newton's second law of motion, which is dp dt equals F net and F net equals ma. I think these are just two different representations of the same equation. And also I use the gravitational force formula, which is g m1 m2 over r squared. And I connected the F net equation for the momentum to the change in momentum, and then connected the concept of having a parallel and perpendicular force to the F net. So for the results preview, these are the part one results of the net force. And then I was asked to calculate the mass of the black hole by part one, and I found that. And then there was the end result from part two, and I got that by plugging in the mass of the black hole that I calculated in part one, and then found the period and the velocity, potential velocity. And then through trial and error, I was able to find the Vx and the Vy of the planet, of how fast it should move around the black hole. So for the initial conditions, these are the constants, and then I had the mass, which was given to me in the question, and these are the part one initial conditions. And then for part two, I just used information from part one and plugged them in, like the mass from the black hole, that was a given, and that was an initial condition. And then I just adjusted the speed, and then for everything else, it was just the computational model that collected it, like the Vx and the Vy. So for the main physics idea, F equals ma is Newton's second law, and then we know that Fg is the F net that's acting on the object. So I just equated those, and then I was able to find the change in velocity and how it changes throughout the path because it's an ellipse. And also I connected the object of V escape and how kinetic energy is just equal to gravitational energy, and then how we can find the V escape over a planet so it doesn't get sucked into the gravitational field or the gravitational force of the black hole. So for the system surrounding, our system is the planet, and the surrounding is just the black hole because it's the thing that's acting on it. And then for the coding, for part one, I matched the initial conditions like the given mass. And then in lines 134 to 144, that was the while loop. I edited the while loop in order to make sure I can calculate delta x, or just the distance, and at any given time, and then use that to find Vx and Vy for the perpendicular and parallel forces. And then for the second part, also I added my email, my contact email, in order to produce unique values. And then after that, I plugged in formulas for momentum, pi equals mv for initial and final momentum. I plugged in the equation for delta v and delta p. I also used Newton's second law for dp dt to find the change in momentum. And also I plugged in how F net is just the sum of perpendicular and parallel forces. And then I used the mass. I plugged in an equation for mass of the black hole in order to find it, which was dp dt over r over gm of the sun, or of the thing that's orbiting around. And I calculated all the values I needed from before in order to get this equation, and then changed the vector so I can get arrows that show how the force changes throughout the motion.
What did I do?
Here's the results.
Energy. So what's going to happen to my velocity here? I have to go to that higher velocity. So the farther I am, the more velocity. If I move it closer.
So that was the result of part one, and here are the F nets that you found. So for part two, I just took the mass calculated from part one. These are the constants that were there, and then I used that to calculate the planet's initial velocity, which I needed. And for that, I just used bh.m, which is just the mass of the black hole. And then through trial and error, I found the Vx and the Vy. And here's a screenshot from the Glowscript and how it was able to escape the path. So for the similarities and differences, the similarities is that both models will show you how like a planet moves around something that has gravitational force, and the speed of the planet will increase when it's closer to the black hole because of the gravitational force, but it'll slow down as it moves further. But for the differences, obviously there's accuracy issues because real life orbits might be slightly different because the model might not consider things like the planet losing energy, and also in the real world there are like way more factors that could affect the motion of the planet, and way more forces that could be acting on it that are just not shown through the computational model. For the possible sources of error, so there might be rounding and calculation errors because Python only counts to like 64 bits after the decimal point. There might be incorrect initial values, and that's because it was found through trial and error, so they might be slightly off. And also there are idealized conditions, so it's assuming that only gravity is affecting the planet, but that's not true in the real world. So what does it mean in terms of motion analysis? So the net force is just the total force acting on the planet, and it's the sum of the parallel and the perpendicular directions, or the forces in the perpendicular and parallel directions. And for us, the perpendicular force is just the force that pulls the planet towards the center of the orbit, and the parallel force is just the part that would change the planet's speed and the change in momentum, if it exists. And it was present for us because it's moving in an ellipse. Also, the rate of change of momentum is just how the velocity changes throughout the path, but the mass stays constant, so the change in momentum is just equal to m delta v. And then the perpendicular and parallel directions. And for the what if question, basically to get into an orbit around a black hole, your spaceship needs to move at just the right speed, because if you're going too fast or too slow, it's just not going to work. It's either going to get sucked in or just fly away. So for that, we can use the v-escape formula, which is just the square root of 2gm over r squared. And that was derived when I was discussing the physics concepts previously. And I found v-escape to be approximately 21,000 meters per second. And yeah, the speed works on the Glowscript. I added it, and it was able to orbit around the black hole. And basically, what the v-escape does, it's a balance of forces, and it makes sure that the energies are balanced and correct and can be used. That's all. Thank you for watching.